You post those on campus, right?
Yep.
Videos?
Yeah, that's under announcements.
Okay.
And then you can stretch it. Yeah. What is the definition of the number is about 0. Distance from 0 to 0. I need to buy myself more color. No, it's just that I get lost if I don't see colors and I get out. I'm so worried. You said what?
Yeah.
It's 0,
Can I have a blue rag? I didn't have one this morning. I was like, oh, I need to start bringing those. I'm going to make a note to bring them from home. All right, folks, let's review these together. What kind of transformations can you perform on a function? And how do you make it move on the graph? And let's write out the formula. So first of all, if my hand is the function here, it's parabola. How can I make a parabola move? Nadine, what's one way? Right and left. Very good. How else, Omar? Up and down. How else?
Stretch it.
Yeah, you could stretch it taller or shorter. Think about that idea. How else?
Stretch it.
Stretch it widthwise, skinnier or wider. And one more, Hector?
Transfer.
Well, we can go up, down, left, right, stretcher, or taller, shorter, and then flip it upside down. Or other than flipping it upside down, you could you could flip it sideways. Okay, so then putting all that together into a formula.
Quick question. Does contraction and extension count?
Yeah. So I'm going to write it slightly different than I have before because you'll see it different ways in different textbooks. But here, everybody, take a look at what I write here. Let's say that I'm talking about a parabola, okay? So y equals x squared. Then what you can say is you can have x moving right or left, and a lot of textbooks will write with that with the letter h. So that's right, left. And then you can go up or down, and a lot of textbooks will use the letter k. So that's up, down. Then you could have the slope out front, that's the vertical compression or expansion, and that's the letter A. And then you could have the flip it upside down, which is the plus or minus. So this is one very common way of seeing it, where A represents your slope term, H is your right left term, K is your up down term, and this is one way that they write it. I've also seen it written as y equals, now in terms of the function, right? So forget x squared, I'll just say any function. You could have f of, so first you have A to represent the slope, plus or minus to represent up or down. On the outside, you would have plus or minus d to represent shifting up or down. On the inside, you could have plus or minus c to represent moving it right and left. But then also on the inside, you could have a b to represent stretching it horizontally. And then that b could be plus or minus as well to represent if you flip it right, left. So, oh my goodness, I mean, there's so many different things going on in here, right? The d is how you move up or down. The c is how you move right or left. The plus or minus out here is whether or not you flip it upside down. The plus or minus in here is whether or not you flip it right side left. Right side left. And then the A is the vertical stretch, whereas the B is the horizontal stretch. Okay, now I realize that's a lot of information, right? That's a lot of information. This is potentially what you might see in the textbook or what the video guy has shared with you in the video. His name is James. Okay, so that's a lot of different ways to express a transformation. The key is not what letter you use, but rather where you're putting the information determines what it means. So again, if it's outside the function, it's vertical movement, moving it up or down, stretching it taller or shorter. If it's inside the function, it's horizontal movement, moving it right and left, or squeezing it skinnier or wider. And then if it's outside again, it's a vertical flip up and down. If it's inside, plus or minus, it's a horizontal stretch right and left. Okay, so those are your different transformations. What is the definition of the absolute value function? So when you write down f of x equals the absolute value of x, what does absolute value of x really mean? What's that? Exactly, it means distance from 0. Now let's clarify one question from the homework real quick, distance from 0. So folks, let's say that you had a problem like this, where it was 5 minus 2 times the absolute value of 3x plus 7, absolute value equals 10. Okay, so everybody with me, Hector? Okay, so you got this problem. There's a couple of different ways you can approach it. One is you just isolate the root. So I'm just going to hold on to the root with my hand there. And I'm saying the root is being multiplied by -2 and adding 5. So I'm going to subtract 5 over first. That leaves me with -2, absolute value 3x plus 7 equals 5. And then the absolute value of 3x plus 7 is being multiplied by -2, so I divide off the -2. And then that gives me the absolute value of 3x plus 7. And now I have isolated the root. Right? So that's what I need to do, is isolate the root. What I don't recommend you do, even though you technically can, is I don't recommend that you distribute the 2 in, for a couple of reasons. If you did distribute in the 2, you'd have to keep in mind that you still have the minus sign out front. All you did was distribute in the 2 to become 6x plus 14. Okay, you cannot distribute in the minus sign. If you wanted to distribute in the 2, you could. It just made the numbers inside bigger. You would still have to subtract off the 5 here, which would leave you with the negative absolute value. And you'd still have to divide, that's a -1 really. You'd have to still divide off the -1. So what did we accomplish by distributing in the 2? Well, we still had to subtract off the 5 and divide off the negative, and now these numbers are just bigger. So honestly, that's fine. You know, whichever way you want to do it. If you wanted to distribute in the 2, you could, but you're still going to have to minus off the 5 and then divide off the negative. You can't distribute in the negative. I really don't think you can. Even if you could, I don't think you should, because then you're playing with fire, right? You're literally about to mix in a negative sign into absolute value. It'd be best just to leave it outside. Okay, so that's just one thought about your absolute value problems. Once it's isolated, then you can say the distance of 3x plus 7 from 0 is -5/2. Well, this is a bad example, because can you be -5/2 away from 0? No. So actually, this problem as I wrote it would have no solution. That's kind of interesting to notice. That if you're saying that your distance from 0 is -5/2, that's impossible. So this particular problem, as I wrote it, has no solution. You cannot be -5/2 away from 0. You could only be +5/2 away from 0. So some absolute value problems have no solution, which makes sense. We talked about this, remember, because when you graph absolute value, it's either above it and there's no solutions, or it's on the x-axis and there's one solution, or it goes below it and there's 2 solutions. So is 0 solutions a possibility? Yeah, and that's what that would look like. If you had the absolute value of 7 equals a negative number, that means your graph would look like this. Okay. What are some synonyms for x-intercepts? Give me one, Valeria. And a synonym for x-intercept. That's fine. Yeah, a root. Very good. Interestingly, I don't know that it refers to a square root. It's just a root. It's just root, because a root could be a square root, cube root, 4th root, 5th root. They simply mean a root. Okay, what's another synonym for x-intercept? Emily? Yeah, a 0 of a function. And what's the last synonym of x-intercept? A solution. Okay, very good. Generally speaking, what do absolute value of x and x squared have in common? And I kind of just drew it right here. What do they have in common? A parabola and an absolute value graph. Go ahead, Gabe.
One solution, 2 solutions.
Exactly. They either have no solutions, 1 solution, or 2 solutions. Very good. And then finally, given a quadratic formula, what are the formulas for y-intercept, x-intercept, and the vertex? So I'm going to draw that in right here. If I have a parabola, then what's my formula for the y-intercept? What's my formula for the x-intercepts? And what's my formula for the vertex? Who'd like to give me the formula for the y-intercept? given that we're all talking about ax squared plus bx plus c. What's the formula for the y-intercept? You all wrote it down, I believe. You all wrote it down in your notes. Yep, it's just c. That's the whole. That doesn't really sound like a formula, does it? It's just a letter. But that is correct. C, the value of c, whatever it is the y-intercept. Okay, what about the vertex? What's the formula for the vertex? Yeah, very good. The vertex is negative b over 2a. That's all you really have to remember from the vertex formula. Because then to get the y value, you just plug that into the function. Okay, so there's our vertex formula. And then what's the formula for the x-intercepts?
It's
The quadratic formula. Negative b plus or minus, well, technically over here, this x-intercept is negative b plus the square root of b squared minus 4ac. And then over here on the left is negative b minus square root b squared minus 4ac all over 2a. Okay, so this whole graphic right here, this whole image is well worth memorizing and writing down over and over so that you remember the formula for the y-intercept, the two x-intercepts, and then the vertex. Okay. That's all I have for warm-up questions. Does anyone want to ask a question about any of that before we keep going? Omar? Right here. Dave?
I went over this with
Lee?
Yeah.
Okay, perfect. Super. That's great. That's what Lee is here for. Nadine? Emily? Valeria. Okay, then let's look at one question online from the homework. I know this one for sure people had questions about, and I'm very sorry I neglected to talk about this example on the more homework. So this is something that when you saw it, you might not have known what to do. So everyone, can you see the graph? Let's talk about what that graph transformation is. So in terms of our transforming abilities, so y equals something squared, which way did that parabola go, up or down? They're not flipped upside down. I mean the vertex itself. Did the vertex go up or down? Up 1, so I'm going to write a +1 here. And then which way did the vertex go, right or left? Right 2, so I'm going to write x minus 2. And then is it flipped upside down?
Yeah.
Yes, there's a minus sign. Now there's one more aspect of a parabola, and that is the slope. Remember, traditionally the rule is the 1, 3, 5 rule. So you would normally go right 1, down 1, right 1, down 3, right 1, down 5. But you can tell this parabola is not following the 1, 3, 5 rule. This is going right 1, down 2, right 1, down 6. So this is following the 2, 6, 10 rule, which means that you took the 1, 3, 5 and multiplied it by 2. There's an easier way to think about it. When you want to know the value of A, that is the number out in front, when you want to know that number right there, you just start at the vertex, you go right 1, and however far you go to get back to the parabola, that's the value of A. So everybody watch, if I start at the vertex, I go right 1, to get back to the parabola, I have to go down 2, that's the value of A. So that even takes care of the fact that it's negative. Because when I left the vertex, I went right 1, down 2, so that down 2 is the number in front. And then just to verify that this worked, let's type it in. Here we go. This is negative 2x minus 2 squared plus 1. And it worked. So I'm very sorry that I did not mention that simple way of thinking of the 1, 3, 5 rule. Of course, you need to know the 1, 3, 5 rule, because that allows you to graph the whole thing. But if you just want to look at a graph and know what the A value is, you just start at the vertex, go right 1, and then however far you get, if you go back to the parabola, that's your A value. So that's the rule that you use for A value. Thank you to those who sent me that question. In general, thank you for emailing me. I'd say about half of you are emailing me. Not everyone's emailing me. And you know what, if you don't have any questions, that's great. But please, if you're sitting at home and you have questions, I hope you email me. Because I just sit at home all night long and I just sit there tapping my fingers on my kitchen counter like, when are my students going to email me? Right? My wife sees me crying sometimes at night and she says, why are you crying, JW? I said, my students are not emailing me. So please send me an email whenever you feel like it. You cannot send me too many emails. You really can't. Some people are like, well, I didn't email you because I didn't want to bother you. I've got people sending me 5 emails a day. All right, so 1 email is not going to break the bank, right? So please send me 1 email, or 5. If you send me 20 emails in one day, I think I'd probably pull you aside. 20 emails, there weren't even 20 questions on the homework. But no, seriously, you can email me as much as you like. That's why you pay me. Okay, so where are we at? Today is February 4th, and we're going to cover sections 2.4 and 2.5 after we finish the word problems from 2.3. I do believe we'll be able to finish that. We'll be back on track, according to the syllabus anyway. And then on Thursday, we cover the last couple of sections, and then on next Monday, sorry, that's not Thursday, that's Wednesday. On Monday, you'll have your first test. Now, your first test, you all have a practice test, right? Let's see here. Here's a copy of the practice test. The practice test, later today, I will post online the solutions to the whole practice test. Okay, that way you'll be able to go online and look at the solutions for the practice test. And remember, this is due on Monday. So, you know, I'm not suggesting you do this, but I mean, you have no excuse not to fill this out by Monday because you can just go online and look at the solution. But don't do that. Just don't just go copy everything down. Try it out yourself. Check your answers against the solutions. But what I am saying is you have no reason not to bring that thing completed with you by Monday because it's one of your grades. What else do I want to say? Email me anytime this weekend if you have questions to get ready for the test. A random note. I don't know if any of you have ever taken a class for honors at Gateway, but this is the last week to sign up for honors, so you just have to sign up by Friday. If you want to do honors, it's really fun. You would take this class for honors or any other class for honors. And essentially, for me, you would do a biography project where you research a mathematician in depth, write up a little biography about them, and then choose one piece of math that they did and go into depth about that math. And I would work with you on all of this. Okay, you have the whole rest of the semester to do it. Isaac Newton is a mathematician, so he counts. Yeah, any mathematician, I'll help you. If you have the interest, you're like, I'm really interested in Duffy Lightnings. You're like, all right, let's do that guy. Right? You could do any mathematician from around the world. Okay, past, present, future. No, past or present.
So,
you just come see me in office hours, and then I would point you to the honors department, which is in the AF building, across the walk there. So you would do research about a mathematician, you'd do some math about the mathematician, and then at the end of the semester, you would do a 10-minute presentation to the class, where you would tell everybody what you learned. You would give them a quick 5-minute bio of your person, and then you'd give a little 5-minute recap of a significant mathematical result that that person came up with. So if you'd like to do that, just come see me this week and we'll get you signed up. Now, keep in mind, I know that sounds super awesome and fun. You're like, who wouldn't want to do that? It is going to be demanding. Like, it will take time. You know, we're not talking about some 2 hours of effort. You're probably looking at 10 hours of just researching the person, another 5 hours of writing up your essay about the person, and then another 10 hours of doing the actual math, because I'm going to walk you through the math and make sure you understand it in depth. So,
reading.
What's that?
Proofreading.
Proofreading. Yeah, and I'll proofread your essay, and then you'll build a PowerPoint, so you can come in here and give a PowerPoint to the class. So it is significant, but here's the deal. The benefit is that when you take the class for honors, depending on how many credits you're taking, like if you're full-time, the honors department pays for this class. So you literally get this class for free. I don't know what could be better than that. By taking a class for honors, provided you're a full-time student, you get the class for free. If you're a half-time student, I think you get half of the tuition paid for. The key is that taking a class for honors credit pays for part of your tuition or all of your tuition. And for that reason alone, like, I would take every class for honors. You just get all of your tuition paid for free. You might, that's a lot to do, but the point is you can do it. So if you're interested, come see me. Either, like, it's not right after class, but you can come see me before class or just email me. Email me your intent. Say, Mr. G, I'm interested. Let's do it. And then the first thing I'll tell you is go choose a mathematician who you like. Tell me who that mathematician is, and then I can help you choose a math idea from that mathematician. Okay? All right, now that brings any questions on honors? Okay. All right. Yeah? The AF building, his name is Andy Leonards. AF building, Andy Leonards. If you just go over there and start saying, Andy, I'm sure somebody will. I'll be using that. Okay, my joke for you today. Now, this is one of my all-time favorite jokes, so whether you like it or not, just laugh. Do you know why you never see elephants hiding in trees? They're so good at it. Like, they're that good at it. There's actually elephants hiding in trees all around campus. All around campus, elephants everywhere. But they're so good at it that you don't see them. Yeah, exactly, that's the joke.
The most like fantasy.
It's what?
The most like fantasy.
Exactly, Dumbo. All right, folks, so here we are. What did we do, number one?
Yeah.
We did number one, right? So let's go ahead and continue going here. What I'm gonna do is help you set up the problems, because then it's just a matter of either, like I'm just telling you right up front, all 6 of these word problems, they're either asking for the vertex or the x-intercept, right? So every single word problem either wants the vertex, which is negative b over 2a, or they want the x-intercept, which is the quadratic formula. So right up front, I'm just telling you that. So let's take a look at some of these questions. Number 2. We didn't do number 2 yet, right? Okay. We've seen this question before, though. They're saying the temperature T in degrees Fahrenheit, T hours after 6 a.m. is given by this formula. So always, you would begin by writing down the formula in your own handwriting. And then you would label the units. So what is the unit of your input little t? No. Little t. Hours after 6 a.m. Hours after 6. And then what's the unit for big T? That's degrees, or the temperature in Fahrenheit.
Question, is this due after
Everything is due, we're going to do those today in class. And you only have to do as much as we do in class. The only thing I'm actually collecting from you are the packets that said chapter 1 and chapter 2. What you're holding in your hand is very important notes. You should write down everything I write down, but I won't collect it. Okay, so likewise, since capital T is temperature in Fahrenheit, this whole thing is temperature in Fahrenheit. Right? So that's what that whole computation will give you. So this is a good best practice, folks. When you begin any word problem, you should definitely write down and label what you're talking about. Right? So now we know what this formula does. Next, yeah,
What did you put 12 instead of 13?
that's a typo. Thank you. I meant 32. Okay, so next thing you want to do is draw a sketch. And again, label your units. This is my x-axis, my y-axis, my input, my output. Therefore, my x-axis is my little t hours after 6. And therefore, my y-axis, my output, is big T, which is degrees Fahrenheit. Now, let's look at the shape of the graph. The graph is a t squared, therefore the shape is a, yeah, it's a parabola, a U shape, but it's a negative t squared, therefore it's facing upside down. So that means you can immediately go ahead and just draw a parabola that's upside down. If we wanted to be more exact about this, you would type it into Desmos and see what the graph actually looks like, right? But generally speaking, you see that it's an upside down parabola, so you can draw an upside down parabola. But if you wanted to, you would just go on over to Desmos or your graphing calculator, type in negative 0.5 x squared plus 8x plus 32. And what does our graph look like? Essentially what we just drew, right? Isn't that more or less what we just drew? It's an upside down parabola. Now, what are they asking for? They say, what is the warmest temperature of the day? So what are they asking for, the vertex or the x-intercept? The vertex. And Desmos already tells me the answer. It's right there. There's the vertex. It's 864. So let's just go ahead and label that. The vertex is 864. What does that mean? What is that? 8? Yes.
hours after 6 a.m.?
Exactly. That's 8 hours after 6 a.m. And 8 hours after 6 a.m. What's 8 plus 6? 14 o'clock? What's 14 o'clock? 2 p.m. And then what does the 64 represent? That's the output, the temperature in Fahrenheit. So remember that when you do a word problem, the question is given to you as a word, but the answer should be a word. So your answer should be a word problem. You'd say you'd say 2 p.m. is the warmest temp of the day, which is 64 degrees Fahrenheit. Right? That'd be our word problem. Now, I just cheated by looking at the graph and getting the answer. How would you actually find the answer? The vertex formula. So the vertex formula is you're looking for the vertex, x comma y. So x is negative b over 2a. So let's find that real quick. it would be helpful to write down what each of your numbers are. So back up to my equation, I would say A is -1/2, B is 8, and C is 32. So now I need to plug that into my vertex formula. So I'm going to write identity, -b all over 2a. And my b was 8, and my a was -1/2. Now something like this you can type into your calculator, but something like that you can do in your head. That's a -8 all over, half of 2 is 1, and it's negative. So that's -1, and the negative over negative is positive, and 8 over 1 is 8. So that agrees with what we found out from the graph. So that's the x value of the vertex. Now the y value, you do f of -b over 2a. Meaning you're doing f of 8. You're going to plug 8 into the function. So if you plug 8 into the function itself, again, you can do that on your calculator. Or you can write it all down. Yeah, that would be -1/2 something squared plus 8 something plus 32. And you would plug in the 8. And then you do the whole computation. So 8 squared is 64. 64 cut in half is 32, but it's negative. And then 8 times 8 is 64. Then plus 32. What can you do with those 32s? One's a -32, one's a positive 32. You just cancel them out, and the answer is 64, just like we expected. Okay, so there we go. As I said, every single word problem, 1 through 6 right here, it's either asking for the vertex or the x-intercept. How do you feel about that one? What questions would you like to ask? Okay. Well then, let's try the next one. And I recommend you do the same procedure. The procedure looks like this. You write down the formula in your own handwriting and you label the units. You make a graph and then you label the units. Then you get a picture of what the graph looks like, either by looking on Desmos or just off the top of your head. And then you actually begin doing the problem. So in number 3, we have some function c of x equals x squared minus 10x plus 27. And it says that represents the cost in hundreds. So I already know c is cost in hundreds. To produce x thousand pens, so I know that x is pens in thousands. And therefore this whole equation, when I compute it, is going to equal what? Pens or cost? Okay, so that's what our formula is. Now let's draw a picture. On my graph, my x-axis, my y-axis, my x-axis is tens and thousands. My y-axis is cost in hundreds. And what is the shape of my graph? Spiral, is it facing up or down? Up. So, not good. You can actually go to Desmos for this. You could say, hey, gosh, I really don't know what my graph looks like. I don't want to risk it. So I'm just going to go plug it into Desmos or my graphing calculator and do x squared minus 10x plus 27. And then you'd look at the graph and you'd say, yep, it's a parabola facing up. And at this point, you would now finish reading the problem and it would say, how many pens should be produced to minimize the cost? So if we're talking about minimum cost, what point are we talking about? And the lowest point is called the vertex. So again, we're just looking for the vertex formula. Now they're asking 2 questions. Notice there's 2 question marks. So there's 2 questions. How many pens should be produced and what is the minimum cost? So let's look at the graph again. I'm just going to cheat and get the answer. The answer is 5, 2. The minimum is 5, 2. How do we interpret that result? 5, 2. What does the 5 represent? Yeah, thousands of pens. So that's 5,000 pens. And what does the 2 represent? Yeah, $200. Okay, so that gives us an interpretation of your coordinate. And then you give a complete sentence. You'd say, How many pens should be produced to minimize the cost? You should produce 5,000 pens to minimize the cost of $200. Okay, but have we actually done the vertex formula yet? No, so far we just kind of cheated to look at the big picture. Now you would proceed to say, okay, the vertex is negative b over 2a, comma, f of negative b over 2a. And you'd say, okay, that's my vertex, you'd say x is negative b over 2a, and you'd write negative b over 2a, and then you go back to your formula, and you'd say, what's my a, b, and c again? A is 1, B is negative 10, C is 27. So now you have your numbers to plug in. So B is negative 10, A is 1, and that gives us negative 10, which is 10 all over 2, which is 5, and is that what we got? Yeah. And then, to find your Y value, you'd say Y is F of negative B over 2A, which just means take that number and plug it into F. So we're going to do F of 5. And again, you can do that any way you like. I would probably write down the formula empty. So something squared minus 10, something plus 27. All right, yep. And I'm going to plug in my 5. And chances are we could all do this in our head, roughly speaking. That's just 25 minus 50 plus 27. And yes, that's 2. So did the vertex formula give us the answer we expected? Yeah.
Did that answer both questions?
What?
Did that answer both questions?
It did answer both questions because we were looking, yeah, the vertex was both questions.
Okay.
The first question was saying how many pens should you produce? That's X. The second question said, what is that cost? And that's Y. Yeah, exactly right. Okay, now folks, I'm a mind reader and I can hear you. You're saying, hey man, as soon as it says minimize the cost, I already know that's the vertex. But it says minimize or maximize, that's the vertex. So I'm just going to take my numbers, A, B, and C, plug it into the vertex formula. Why do I need to do all this writing down the function and labeling the units and making my graph? Yeah, it's all about comprehension, right? I mean, anybody, I suppose, could just say, well, that's my A, B, and C. I'm just going to plug it into the vertex formula and wing it. But I really don't hope you wing it. You know, pretend somebody's life is on the line. Which, if you have a job, chances are somebody's life is on the line. You know, manufacturing cars that are safe, or being a doctor doing surgery, somebody's life is always on the line. So you'd want to be careful. Folks, any questions about those? Then let's take a look at one that's a little different. First of all, let me just tell you, I'm gonna let you do 5 and 6 on your own. Okay. Everyone take a look at number 5. Oh no, I want to do 5 with you. Okay, number 6 you can for sure do on your own. So just circle 6 and write homework next to it. 6 is your homework because they give you a function and it says when does it reach the maximum height. So what do you want, the vertex or the x-intercept? The vertex. So number 6 you can just say do for homework and you're looking for the vertex. No, I'm not going to do 6 with you. You can do 6 for homework. So circle and write homework and write vertex. So let's try one that's a little different. Number 4. Everybody, I want you to look at number 4. And first of all, does it give us a formula? No. Now that means that word problem is a little more complex. Because instead of just giving you the formula, they want you to create the formula yourself. And what that tells you right up front is it's going to require a little more work. So let's go ahead and start. Well, everybody just read number 4 on your own. Read it through and see what the problem is about. Read number 4 and see what it says. So just generally speaking, if somebody said, hey, what is number 4 about? What is it about? Very good. Finding the dimensions of a garden, right? We're talking about a garden, and we're talking about the perimeter of the garden. We're talking about the area of the garden. And the question says, what are the dimensions of the garden that will maximize the area, and what is the maximum area of the garden? So we're just talking about building a garden. So let's start together and draw a picture together. Starting from the beginning, it says, Skippy wishes to plant a vegetable garden along one side of his house. So everybody draw a house, and then along one side of the house, draw a garden. So we have a house, we have a garden. The garden is built along one side of the house. In his garage, he has 32 feet of fencing. So that means that this side plus this side plus this side has to add up to 32. Would someone like to give me an example of 3 numbers where these two are the same, right? These 2 numbers are the same. Give me 3 numbers that add up to 32. One more.
10, 12, and 10.
10, 10, and 12. Very good. So everybody, do you agree that this is one possibility? You could build 10, 10, and 12. And if he did do that, what would be the area of his garden? The area is length times width. So that would be, I'm just going to call this width, and I'll call this length. So that'd be 10 times 12, which is 120. Thank you, Omar. Somebody give me another pair of numbers, or a triple of numbers that will work. What else could those numbers be? What is it? 9 and 14? I think that would work, right? If we did 9, 9, and 14, then 9 and 9 is 18, and 18 plus 14 is 32. Okay, that works. And now the area is going to be 9 times 14, which is 126. So far, which one gives better area? Yeah, this one. Because we want as much area as we can get. The more area we have, the more plants we can plant, the more crops we'll have. So we want to maximize the area. Well, is that the maximum area? We don't know. We've come up with 2 examples. But now what we'd like to do is know for sure what dimensions give the most area possible. So here we go. Everybody ready? This is how you set up a problem like this. How wide is that? X, right? If you don't know, you just write X. So call that X and call that X. Because theoretically, it's the same measurement. Now, how long is that? Sure, we can call that Y. Everyone take a look, call that Y. Now, what do we know for sure about this plus this plus this? It adds up to 32. And what we'd really like is to rewrite Y in terms of X, because we don't want 2 variables, we just want 1 variable. So what do? 1x plus 1x is 2x plus y equals 32. And then y is being added by 2x, so we subtract the 2x. And we get y is equal to 32 minus 2x. So now, instead of writing y right there, let's write down 32 minus 2x. That's how long that side is. So far, so good. We have the dimensions of the garden in terms of a single unknown. Hector, you need to stand up. All right, you're drawing the diagram with us? All right, so now what, folks? We want to calculate the area, right? So now area, which is length times width or base times height, however you want to say it. Now we're just going to go ahead and multiply x times 32 minus 2x. Right, x times 32 minus 2x. And now what? Yeah. Yeah, we want to distribute. Keep in mind, we expect to see a quadratic. And so quadratics go x squared to x, no x. So we want to see a quadratic, so we distribute. And that gives us that the area is 32x minus 2x squared. But we want it to look like a normal quadratic, so what do we need to do? Rewrite it. Yeah, negative 2x squared plus 32x plus 0. Because there's nothing there. Yeah, why not? Just to make it look like ax squared plus bx plus c. Yeah, that's right. That would be the y-intercept. So we finally now, we've done all this work to get to the point of what we would have had if they had just given us the formula, right? So we had to do all that work ourselves to get the formula. Okay, so now we would finish the problem just like we already had been doing. We would say, this is really a function, so area is a function of x, where x is my width. And I would say, I know that my a value is -2, my b value is 32, my c value is 0. I know that my input is width. I know that my output is area. And I could begin thinking about my graph where this is x is width and my y is area. And what will my graph look like? It's an upside down parabola. So we'd have an upside, and as Dave just mentioned, the y-intercept is 0, so it'll be an upside down parabola like that. And the question says, what are the dimensions of the garden that will maximize the area? So what are we looking for? The vertex. We want the vertex, which we just plug this now into our formula for vertex. And then they say, what is the maximum area of the garden? Well, they want everything. They want to know everything. So you would go ahead and do the vertex formula, which, let's do it together. We've got the vertex. The x value is negative b over 2a, which is negative b over 2a. I already know that my b is 32. My a is negative 2. So that's negative 32 over negative 4, which is 8. Negative over negative is positive, and 32 divided by 4 is 8. Now my y value of the vertex is f of negative b over 2a, which just means plug that number into the function. So I'm going to plug 8 into the function. And if I plug 8 in there, whether you do it on your calculator or just by looking at it, that'll be negative 2 times 8 squared plus 32 times 8. A lot of computation. I would use my calculator. So that gives us 32 times 8 minus 2 times. I got 128. Did anyone else get 128? All right, so now let's label that coordinate on our graph. That's the coordinate 8, 128. Now what does the 8 represent? And notice if you labeled your graph, this answer should just come to you like that. What does the 8 represent? The width, right? Because we labeled everything. Input is 8 is the input, so that's the width. That's that width right there. So now I know that back on my garden picture now, I can go ahead and say x equals 8. X equals 8. Now, what does that mean y is? If I plug in 8 for x, 2 times 8 is 16. 32 minus 16 is 16. Yeah. Again, you can just plug that into your calculator. So, what are the dimensions of our garden?
8 by 16.
8 by 16. And the area is the output. So that gave us the whole problem. Now, folks, this is a gloriously long problem, right? It's not even all that long in perspective of math problems, but it's a good problem because you had to go all the way around the block to get there. You had to start with a picture, build your own formula, get your formula, do the vertex formula, find your input output, and then interpret the input output back on your diagram as the width and then the length. And so your final answer would say an 8 by 6 garden has maximum area equal to 128 feet squared. And again, it's a word problem because they expect the answer in words. Did we respond to all parts of the question? Yeah. So you know how a lot of times in mathematics, it seems like the mathematics is all about the formulas, right? Like how to plug numbers into a formula and compute answers. That's not really what math is about. Math is about interpreting what you just did. Being able to draw a picture, come up with your own formula, you do some math formulas, and then you interpret your final answer. Okay, well that was number 4. Let's do one more together. We'll do number 5. Go ahead and read through number 5 and see if you can answer for yourself if they're asking for an x-intercept or a vertex. Read the problem and see if they're asking for an x-intercept or a vertex. Yeah, number 5.
We answered or we?
You can answer it. Go ahead, Dave. It is an x-intercept. Let's read the problem and find out. It says the height of an object drop off the roof of an 8-story building. So there's me holding an object. I'm going to drop it. Is modeled by h of t. H of t equals -16 squared plus 64. Where h is the height. That's in feet. Height in feet. And t is seconds. There we go. And what am I computing? This is height. And then I can have my graph. And again, my input is seconds. My output is height. And you'll notice it's an upside down parabola. And the y-intercept is way up at 64. So I'm going to draw something like that. Well, no, that's not what I want. Well, it doesn't even matter what you draw. I mean, it could come straight down or it can go up first. So you have a parabola, and it's saying how long before the object hits the ground. So where does the object hit the ground?
X is 0.
Yeah, right there. Well, not when x is 0, when y is 0, when the height is 0. And therefore, we're looking at the x-intercept. So yeah, this problem, we're definitely wondering about the x-intercept. We already know the height when it hits the ground, the height is 0. So we're really just interested in time. At what time does the ball hit the ground? So on the one hand, we all wrote down that the x-intercept formula is the quadratic formula. But there's an easier way to do the x-intercept. Remember, the x-intercept is anywhere f of x equals 0. And in this case, it could be easier just to set f of x equal to 0. So take a look at your f of x. Your f of x is just -16t squared plus 64. And if you set that equal to 0 and solve, that's going to give you your x-intercepts. And that's just a 3-step algebra problem, as opposed to the quadratic formula. So what do we do first? T is being squared multiplied by -16 and adding 64. Subtracting 64. So now we have -16t squared equals -64. T is being squared and multiplied by -16. And divided by -16. And now t squared is equal to 4. So t is being squared. So we square both sides. And that gives us t is equal to plus or minus 2. Remember, anytime you do a square root in the course of algebra, the answer is plus or minus. But in this particular case, t is equal to +2 or -2. Does -2 seconds make sense? No. So we cross that answer out and we call it extraneous. Extraneous means the algebra led us to that number, but it doesn't make sense in the context of the word problem. So t equals 2. Again, to answer the question, how long before the object hits the ground?
2 seconds.
2 seconds.
Is there another way going about the situation as well?
You can do the quadratic formula.
What if you were to break it up into, what if you were to factor it?
Oh, you can certainly try to factor it, folks, if you were in the mood. And by the way, today's lesson is on factoring. So after today, we will use factoring as solution or as techniques in our class. I hadn't done factoring yet because we haven't reviewed it formally. But if you had this, and then you brought out the -16 to be t squared minus 4, and then you can divide off the -16. Is that what you mean, Lee?
Yes.
So now you have t squared minus 4. Now from here, you still have one of two choices. You can just move the 4 over, and you'd have t squared equals 4, and then square root both sides, and you still get t plus or minus 2. Or if you wanted to, which you'll be able to after today, you can factor t squared minus 4 into t minus 2, t plus 2. And then, by the zero product rule, this times this equals 0. So either t minus 2 equals 0 or t plus 2 equals 0. Is this what you're talking about, Lee?
Yes.
Yeah, you could do it this way, and you can still end up with t equals 2 or t equals -2. If you just watched that and didn't like it, don't worry about it. Because we're about to cover that today. Yeah. Okay, so we did 4, we did 5, number 6. I said circle and do it for homework. So I still expected you to do number 6. Make a note to yourself, 6 is homework. You can email me about it later today. Go see Lee during the study time at the Learning Center. Come see me during office hours, but number 6 is for you. All right. So I'm very excited. Today's lesson is about factoring, which, by the way, is every mathematician's third favorite F word. Fractions, word problems, factoring. So factoring is actually really wonderful. It's an amazing tool. It's an incredibly clever solutions. It's an incredibly clever solution that mathematicians came up with to deal with some very challenging problems back in the 1500s, 1600s, and probably people knew about factoring long before that. But it really became a common tool around the 1600s, let's say. So, to lead up to the idea of factoring, I'd like us all to play a game first. And in fact, what we're going to do is gamble. We're going to bet all of you $100 on a guessing game. If you win, I will pay you $100. If you don't win, you don't owe me $100.
This sounds like we're at the casino.
Yeah, exactly.
Well, there's actually a casino thing with MIT. There's a casino thing for MIT.
You wouldn't do that unless you use.
Yeah, basically nobody owes you a house.
Oh, I see. All right. Okay, so here's the game. I'm offering you $100. I'm thinking of a number, actually I'm thinking of two numbers, that add up to 10. And all you have to do is guess one of my numbers correctly, and I'll give you $100. So what two numbers am I thinking of that add up to 10? Yep. What?
91.
9 and 1, good guess, is not the numbers I was thinking about.
95.
Not the numbers I was thinking about.
There's not enough kids in class for us to do.
Well, 6 and 4. I'll let you guess multiple times.
Maybe 2.
What else?
Did we say between 1 and 10 or just any number?
I said any two numbers that add up
Oh,
to 10.
well, in that case, yeah. Like 100 minus 9.
Yeah, it could be 100 and plus negative 90.
Yeah.
Right? It gets worse than that because those are still whole numbers.
Yeah. Oh, yeah, you can use it down to 1.5.
Yeah, exactly. It could be 1.5 and 8.5. It could be worse than that. It could be, negative 2/7.
Did you have a number?
And it, no.
I
I didn't even need to. The point is, would you ever guess? Like if I really thought of some random things that added up to 10, you would have a 0 probability of guessing it correctly. I was never going to lose my mind. Okay, now what about this game?
Wins.
Yeah, the house wins every time. So now what about, I'm thinking of two numbers that add up to 0. Same thing. If you can guess even one of my numbers, you win. So what are my two numbers that add up to 0?
Infinity, negative.
What?
Infinity, negative infinity.
Well, unfortunately, infinity plus negative infinity could add up to a number. So what's an example?
1 minus
Yeah, 1 and negative 1. That adds up to 0. What else?
2 negative 2.
Negative 2. 0.5 and negative 0.5. What's that other thing?
So there should be
Yeah, goes
No,
on.
bro.
Yeah, you,
We're looking at
Negative 1/2 minus negative 1/2.
yeah, it could be 1/2 plus a negative 1/2. Those are two numbers that add up to 0.
They're absolute value.
Sure, I mean, you could probably do lots of different things. The key is, would you ever actually guess my numbers? No. Okay, your chances are nothing. Okay, now, third game, and I'm not betting money on this because I know you'll be able to do it. Now I'm taking your two numbers that multiply to equal 0. And all you have to do is guess one of my numbers. 5 and 4.
1 and 0.
Infinite multiplied by 0.
Infinity times 0 can sometimes equal a number. But yeah, one of them has to be 0, right? Okay, is everyone absolutely convinced that if you have two numbers that equal 0, one of them had better be 0? And that's a fact. Now, this thing is called the zero product rule. So everybody, somewhere on your paper up at the top there, go ahead and write down the zero product rule states that if x times y equals 0, then x equals 0, or y equals 0, or both. Yeah, so this is what's called the zero product rule. It's a very simple and obvious idea, but it really allowed a huge breakthrough in mathematics for mathematicians to answer questions like this. So let's say you had x squared minus 7x plus 12 equals 0. Okay? Now I just want you to imagine that I'm asking you to guess what number can I plug in for x to make that thing equal 0? So can I have someone guess a number? If you know the answer, don't tell me the actual answer. I want you to guess. 50? I didn't care to calculate that, Dave, but okay, 50 squared minus 7 times 50. Oh, that's a small number.
Oops.
So now this is going to be 2,500 minus 350 plus 12. So that's going to be 2162. So is that equal to 0? Okay, no, definitely not. Anybody else? Guess a small number. What? Guess a different number. 2, okay. 2 squared minus 7 times 2 plus 12. So it's 4 minus 14 plus 12, which is negative 10 plus 12, which is 2. Is 2 equal to 0? No. Okay, so the point is, if you were just guessing, how long would it take you to guess the right answer? Very long time. Now, Emily, you did guess one of the answers. 3. 3 squared minus 7 times 3 plus 12 is 9 minus 21 plus 12, which is negative 12 plus 12, which is 0. And so 3 was a correct guess. Now, the highest exponent on x tells you how many solutions there are. So we should still have a second solution. If one solution is 3, what's the other one? Oh, sure, let's try negative 3. If I plug in negative 3, does anyone else have a guess after this? Because it's wrong. 9 plus 21 plus 12, those are all positive numbers. They add up to a lot, maybe 41. You said 6? Okay, try 6. 6 squared minus 7 times 6 plus 12. 36 minus 42 plus 12. But that's negative 6 plus 12, which is 6. And that's not equal to 0. Okay, so is everyone convinced that guessing is a bad way to do this?
I see.
Yeah.
I just thought that. Try to multiply something 1 without using 1.
Yeah, you have to use fractions. Yeah, you can do it. Yeah. Okay, so folks, now let me tell you why this is such a hard problem. This is a hard problem because it's an addition problem. Okay, this is something plus or minus something plus or minus something. And as I showed you before, addition problems, can you solve addition problems for guessing? No. Okay, so what we want to do is change this addition problem into what kind of problem? We want to turn it into a multiplication problem. Because if you just have a bunch of things adding to 0, you can't guess it. I mean, you can, maybe, but it's so unlikely. Whereas if I can rewrite this as a multiplication problem, then I can solve it for sure. So first of all, I know you've all seen factoring before. The answer to this factoring problem is that you say, what multiplies to make positive 12 that adds to make negative 7? So what multiplies to make 12? First of all, 1 and 12, 2 and 6, 3 and 4. This is called a factor table. Now, which of those will add up to 7? 3 and 4, but we're saying what multiplies to make a positive 12? It has to be a plus times a plus or a minus times a minus. So what do the signs need to be on them at 3 and 4? Yeah, minus and minus. Now, I have the answer. What multiplies to make positive 12 that adds to make negative 7? Negative 3 and negative 4. And you can check. Negative 3 times negative 4 is positive 12. Negative 3 plus negative 4 is negative 7. So you take these numbers right off your factor table, and you rewrite this addition problem. This is so important. You're rewriting an addition problem as x minus 3 times x minus 4. And now this is a multiplication problem. Okay, this is the core philosophy of what we're doing. We're taking an addition problem, which is unguessable, and we're turning it into a multiplication problem, which is immediately guessable. Okay, so now that I know that this times this equals 0, I'm absolutely guaranteed that either x minus 3 is equal to 0 or x minus 4 is equal to 0. It has to be. And I solve both of those, and I say, hey, x is 3, which Emily guessed, or x is 4, which also works. So to get back to this big picture idea, factor, everybody's third favorite F word. Why do we factor? First answer you can give is it turns an addition problem into a multiplication problem. So if somebody's walking down the street, they're like, hey, why do we learn factoring anyway? You'd be like, well, no, I'm not. We turn addition problems into multiplication problems. And they'd say, so what's the big deal about turning it into a multiplication problem? And then he'd say, the zero product rule states that if you have a product equaling 0, then one of the two products or one of the two parts is equal to 0, and then you can solve the problem. This is a really big deal. So everybody, let's start by doing one problem together. Number 3. Let's look at number 3, and then we'll take a break. But I just want to wrap this idea up so we all understand the philosophy about why we factor and why factoring is so important and not at all just some silly, lame idea that we have to practice a lot. Factoring is huge. It's such a good idea. Okay?
So we would just look at the C, or what's on C? Yes.
You say what multiplies to make C that adds to make B.
Okay.
Yeah. So everybody take that first problem. It says x squared plus 8x plus 12. And everybody go ahead and just write equals 0. Okay, I'm giving you the big picture right now. How would we solve this equation? Now remember, this is a very meaningful question. This is a meaningful question. It's a parabola, and I'm setting it equal to 0, which means I'm solving for an x-intercept. Okay, this is a very meaningful question. I took a function, I set it equal to 0. I want to solve for x because that way I'll know my x-intercept. So what do? This is an addition problem. Let's just say you're never going to guess. That you're never going to guess. You can start guessing, but not a good use of your time. So instead you say, what multiplies to make 12 that adds to make 8? And you make a little factor table real quick. You say 1 times 12, 2 times 6, 3 times 4, that's all of them. And then you say, which of those adds up to 8? Yeah, 2 and 6. Now we're multiplying to make a positive 12, and when you multiply to get a positive, it has to be plus times plus or minus times minus. We do want it to add up to 8, so it is going to be plus and plus. And I do recommend you put in that work there. So the answer is, this addition problem gets rewritten as a multiplication problem, x plus 2 times x plus 6. That's philosophically and conceptually huge. We just turned an addition problem into a multiplication problem. Because now that this times this equals 0, I know that one of those has to be 0. And now you can draw little arrows, and you can say either x plus 2 is equal to 0, or x plus 6 is equal to 0, and therefore x equals -2 or x equals -6. And again, now you'd want to finish the logic in your head. What does that mean? It means that if I take something squared plus 8 something plus 12, if I plug in -2, what will happen? Yeah, it will equal 0. That's going to be 4 minus 16 plus 12, which is -4 plus 12, which is 0. Or if I plug in -6, that'll be 36 minus 48 plus 12. 36 minus 48 is -12 plus 12, which is still 0. One more step to complete the logic. What is -2 and -6 on the graph? Those are the x-intercepts. So we draw a graph over here, -1, 2, 3, 4, 5, 6, and there's my parabola. So you see, factoring is a really, really, really powerful idea. That the ability to turn an addition problem into a multiplication problem immediately allows you to solve for x, which is your x-intercept. And now you know where the graph is. So what we're about to do for the rest of today is look at tons and tons and tons of quadratics and even some cubics and figure out how to turn an addition problem into a multiplication problem. How do I factor this thing? Now, by the way, we're also going to do a lot of factor tables, and so we should notice that a factor table, like let's do the factor table for 20. Yeah, you start with 1, then you go to 2, then you go to 3, then you go to 4. You just check all the numbers. So 1 goes in 20 times, 2 goes in 10 times, 3 doesn't go in. 4 goes in 5 times, 5 goes in 4 times. That's a duplicate fact. I'm done. So that's how you make a factor table. You just keep trying all the numbers until you get to a duplicate, and then you're done. This is your factor table. To factor means to rewrite as a multiplication problem. To factor the number 20 means to rewrite it as a multiplication problem. To factor a polynomial means to rewrite it as a multiplication problem. So we use the word factor, everyone's their favorite F word, in both ways. Actually, it only means one thing. To rewrite as a multiplication problem. To rewrite as a multiplication problem. Okay, this is very exciting. Can't wait to keep going, but I should take a break because my boss always tells me I'm supposed to give you guys a break. So it's 1:35. Let's come back at 1:45. Yeah.
Can you call whoever you need to?
Oh yeah, sure. Let me try that. Yeah, that's very unfortunate.
I was gonna think about it.
Oh, I don't know how to. I don't think it's even in the room. But yeah, I'll call.
I appreciate it.
Are you guys doing?
What minute? Oh, yeah, yeah, we'll get to that. Yeah. What's my favorite method? The fastest method. I mean, the first one is the most basic. Just what do you multiply? Multiply to get C that adds to make B. But that's only if the first term is A. I mean, if A equals 1. Right. But I mean, oh gosh, I mean, I do know what you're saying. There are lots of ways to factor. And my favorite methods are the one I'm about to teach in class. So when class is over, I'd love to know what your favorite methods are. Because I know that there's like a box method, and there's all sorts of other methods that allow you to kind of guess the answer. But what I'll be showing always relies upon the factor table. I did the factor table. Oh yeah, okay, sweet.
But I have students do that. They do this kind of thing where they do, it's crazy, they're doing 20, they'll do this crazy like tree deal and have no idea what they're doing with that.
Oh, I know.
And then I try to guide them into doing the factor table itself. It's just, to me, it's easier to work with because then you can see everything.
Yeah.
I need to make a phone call to the VA.
Yeah, yeah, go ahead. Omar, how you doing?
Ready?
Super duper.
So in this case, I would factor 2, right? So I
Yes.
would make it 2 equals 0. Now it wouldn't equal 0, so would it be like a false answer?
Well, that's a really good point there, Omar. I mean, as it is, this is not an equation because there's no equals 0. So this is not even a zero product rule yet. But if we do go ahead and put the equals 0, and then here we write equals 0, then what we're saying is that either this, or this, or this is equal to 0.
Yeah.
And since 2 obviously can't equal 0, it's just not even part of the problem. But n plus 6 could equal 0, and n plus 1 could equal 0. So you finish solving those answers for -6 and -1, and then you say your solution to -1, -6. The thing is that since this is just an expression, it's not set equal to 0, our only goal right now is just a factor, and that is factor. If it were equal to 0, that's when you'd finish the problem by pointing out what the different parts would be. But as it is, like you would just take this thing, you'd factor out the 4, first of all, so n squared minus 10. And then you factor that, and you'd say that it's 4 times n minus 10 plus 1. And then at that point, you'd just be done. You'd say, this is factored.
So no explanation?
Correct, because this particular problem doesn't say equals 0. It's only when it's equals 0 that you're solving for an x-intercept, after all. On our graphic, what we've been learning is that when you set f of x equal to 0, that's an x-intercept. And is this thing set equal to 0?
No.
No, so they don't fit.
No.
So really all of this is just to practice the idea of factor. So that is completely factored. What that means is I took this addition problem and I turned it into a multiplication problem. Because now instead of something plus something plus something, I have something times something times something. Yeah, good question.
And then for my homework, where was I wrong?
Where were you wrong?
Yeah,
On what?
For the questions I asked of graphic.
Did I respond to you?
Yeah, no,
Oh, well, go look at it. I don't remember off the top of my head. Can you pull it up on your phone or something?
I can try, but I forgot my info.
Oh, your password? Okay, well here, let me see. Maybe I can log on. I can get on my computer, I think. All right. So, Omar, here's your class. Here's the message you sent me. There's 1.7. Take a look. Oh, I did respond. This doesn't show the reply.
No.
It would just be a matter of using parentheses. Here, I'll just hit reply. That way we can look at it. So like this one, you're absolutely correct that it's upside down. And it shifted to the left, so it'd be x plus 1. And then it shifted down 2, so it'd be minus 2. That's what it did. You'll notice what you have here is so close to that, but you have x squared plus 1. It's supposed to be x plus 1 squared. You see the difference? Yeah. What you wrote is x squared. And then
That's what the function was, x squared.
That's correct, but the right and left movement has to go inside with the x.
Oh.
Does that make sense?
Yeah.
Okay, super. Yeah, but yeah, when you log on finally, you'll be able to see the message.
You're just factoring, right?
Yeah, right now we're just factoring. That is correct. Yeah, good job too. I like how you foiled it at the end to check that you were correct.
Yeah, I have a lot of practice before.
Ah, well, very good.
Is that 0? Okay. So your answer would be 0 to negative. Yeah. Well, it's not negative, it's just that's the line. So, say, x equals
Snacks. What did y'all bring me?
You want some M&Ms?
I always want M&Ms, but no, I'm not going to eat them. But of course I want them.
how did you split $100 between 6 people?
Carefully. Oh, yeah.
Why, that's so much better.
All right, folks, so let's dive in. We're going to do some factoring practice. We're not going to finish all the way through a problem. Like, we're not going to actually set it equal to 0 and do the 0 product rule. We're just going to focus on how do you convert the addition problem into a multiplication problem. And then as we proceed through class, we'll be put in those contexts where we actually do it. So what I'd like is for everyone to practice the method I'm about to show you with the acknowledgement that there are other ways to factor that I've seen. I've seen people use a box method. I've seen people use a guessing method. I'm going to teach the factor table method. So everyone, let's start by looking at number 5. And everyone write it down in your own handwriting. B squared minus 7b plus 10. Now let's ask the question. And I'm always going to write it down in the same way, so it's very consistent. We're asking, what do you multiply to make positive 10 that you add to make negative 7? And I recommend that you write those little symbols above the numbers to help you remember what you're asking. What? Yes, that is correct. What do you multiply to make positive 10 that you add to make negative 7? Next step, you make the factor table. So you start with 10. You say, okay, I'm multiplying to make a positive 10. So you just start going through the whole numbers and say, okay, 1 goes into it 10 times, 2 goes into it 5 5 times, 3 doesn't go in, 4 doesn't go in, 5 goes in 2 times, but that's a duplicate fact, so I'm done. That's my factor table. Now I remind myself that to multiply to make a positive number, it's either a positive times a positive or a negative times a negative. Right? That is a possibility. That you could multiply to make a negative a positive 10 by doing negative 2 times negative 5. And in fact, that's what we need in this case. We need the numbers to add up to negative 7. If I just did 2 plus 5, that would make positive 7. I want negative 7, so it has to be negative 2 minus 5. And then you write that in there, the minus and the minus, you circle it, and you say, okay, that's my answer. That's how I factor this problem. So you simply get to write down e minus 2, e minus 5. I'm literally taking the numbers right off my factor table. So where does the work for this problem happen? On the factor table. The factor table is where you do your work.
So you actually have to write.
Oh yeah. I mean, I'm going to write it every single time, and I would expect you to as well. Again, if you have some technique that works for you in a 100% consistent manner, then you could do that if you like. But the way I'll be showing involves a factor table. Okay, number 7. Let's look at number 7. This is the fundamental game that we're playing. Okay, so number 7 is b squared plus 6b minus 40. You start by just labeling the problem. You say, what do I multiply to get negative 40 that I add to get positive 6? So now I make my factor table. I say, okay, my factor table is for negative 40. How do I multiply to get 40? Now again, here, you just start, I use my fingers and I just start counting out. 1 goes into it 40 times. 2 goes into it 20 times. 3 doesn't go into it. 4 goes into it 10 times. 5 goes into it 8 times. 6 doesn't go into it. 7 doesn't go into it. 8 goes into it. But that's 8 times 5, and that's a duplicate fact. As soon as you get to a duplicate fact, you can be done. Okay, so there's my factor table. Now, if that just doesn't come to you by just running through whole numbers, use your calculator. You know, you can just sit there with your calculator and say 40 divided by 1, 40 divided by 2, 40 divided by 3, 40 divided by 4. You just keep going until you finish your factor table. Okay, now, I want to multiply to make a negative number. You can do that by multiplying a positive times a negative, or a negative times a positive. The point is that one of the numbers has to be positive and one of the numbers has to be negative. So what pair of numbers do I choose so that they add up to 6? Yeah, it's going to be 4 and 10. What you can look for, because 1 is plus and 1 is minus, you're looking for which pair of numbers subtracts to make 6. And if you do 40 minus 1, that's 39. 20 minus 2 is 18. 10 minus 4 is 6. 8 minus 5 is 3. 6 is definitely the difference you're looking for. So we know it's 4 and 10, and we want it to add to a positive 6. So which one's negative and which one's positive? Yeah, negative 4 and positive 10. That is the answer. You just get to write down two parentheses, and you write b minus 4, b plus 10, and you're done. This technique of factoring is just called the factor tree, or the factor table method. I don't know that it really has a name. I mean, I think this is just the official method. This is what is in textbooks. Okay, so let's try one more, number 9. We have n squared minus 5n minus 14. And again, we begin by asking our fundamental question, what multiplies to make negative 14 that adds to make negative 5? Now you notice I'm being very careful. I don't just say what multiplies to make 14 that adds to make 5. I'm saying the signs of the numbers, because the signs make a big difference. So what multiplies to make negative 14? I make a factor table for negative 14. So I'm counting up from 1, that's 1 and 14, 2 and 7, and we're done. Because 3 doesn't go into it, 4 doesn't go into it, 5 doesn't go into it, 6 doesn't go into it, 7 goes into it twice, but that's a duplicate fact, so you're done. Furthermore, it's a negative 14, so that means it has to be a positive times a negative. So one of them is plus, one of them is minus, and which pair will add up to negative 5? Yeah, the 2 and 7, which is positive, which is negative? Yeah, positive 2 and negative 7. Again, where are we doing all of our work? On the factor table. When we come back over here, all we're doing is just reporting our answer. We're just reporting what we found out. N plus 2, n minus 7. So that is the basic technique, basic factoring. You'll notice back at the beginning, it says basic factoring only works when a equals 1.
What a are we talking about? Ax squared plus bx plus c. So you can only use this technique when a is 1. You'll notice that for all of these problems, the squared term is just the squared term. There's no number in front of it. The number in front of it is a 1. Okay, so that's basic factoring. Remember, factoring means rewriting an addition problem as a multiplication problem. So now, there are a couple other things that come up. One is, what if the first term, what if a isn't 1? Hector. I'm sorry, I skipped over those. We can come back to that. I mean, we're about to do it, as a matter of fact. Yeah, we're about to do the first couple of problems. So, what if the first number is not a 1? What could you do? Do what? Yeah, take out a common factor. Exactly right. And Hector, thank you. That's what the first couple of questions were. It's taken out a common factor. We can just skip it and move on to these. So, what can I take out of a 2, a 14, and a 12? Just a 2. What can I take out of 4, 36, and 4? 4. What can I take? Well, 2, and this one also a 4. Okay, so we're taking out a common factor. Let's just practice one of these. If you have the problem number 11, and it was 2n squared plus 14n plus 12. First of all, I just want to convince you, you cannot just dive in and start saying what multiplies to make 12 it adds to make 14. Because if you tried that, the factor table for 12 is 1 and 12, 2 and 6, 3 and 4. Could any of those add up to 14? No. So you might, if you did that, you might say, oh, well, gee, this one's not factorable. But that's because you didn't take out the 2 first. So if we take out the 2, let's be very careful. When we use the English take out a 2, like you're taking an apple out of your backpack, take out the 2, what are we really doing? What mathematical operation? Add, subtract, multiply, or divide? We're dividing. We're dividing each of those by 2. So 2 divided by 2 is 1. 14 divided by 2 is 7. And 12 divided by 2 is 6. Right, so when you take out a number, you're really dividing. Which gives us another synonym for factoring. Oftentimes people will say factoring means dividing. But is factoring dividing? Not technically. Factoring is rewriting as multiplication. But we did factor out a 2, which to do that, you divide it out of each term. Now at this point, what multiplies to make 6 that adds to make 7? 6 and 1. So maybe you can just do that in your head, and you go ahead and just report your answers. You say n plus 1, n plus 6. And now this is factored.
Oh, you slip the 2 in front of it?
Yeah, you leave the 2 out in front. Yeah, because after all, the 2 is still there. It's still part of the problem. And now this is called completely factored. And notice, look at the original problem. Something plus something plus something. Now watch. Something times something times something. That's a huge philosophical shift. We go from an addition problem to a multiplication problem. Let's try, well, we don't have to try any of the other ones. The point is, take out a common term. If you have a common term, take it out. That's enough. So how about the next step? What if the first term is negative? Are you allowed to use the basic factoring rule if the first term is negative? No. You're only allowed if the first term is 1. This is not 1, this is negative 1. Yeah, it's an invisible 1, but it's negative. And you're not allowed to do the basic technique if there's a negative 1 out there. It has to be a positive 1. So what do? We factor out the leading negative 1. We call this take out the leading negative. See it? Take out the leading negative. This we call a leading negative. The first term in a polynomial should always be positive. If there's a negative, you have to factor it out. So let's see how to do that. Let's just do number 15. When the first term is negative, negative 1x squared plus 1x plus 90, what we're going to do is you're not taking out a number like 2 or 4, you're taking out the negative 1. And just like when you took out the 2, you're dividing, right? You're taking each number and you're dividing it by 2. Likewise, you're going to take each number and divide it by a negative 1. So it just changes the sign. If you take each of these and divide by a negative 1, what does that do to the sign of each number? It just changes it. So by taking out that negative 1, each sign, negative plus plus, becomes the opposite, positive minus minus. So what we really have now is a negative out front of x squared minus 1x minus 9. That might have looked like a lot of complicated mechanics, and I showed a lot of work. All we're really doing is pulling the negative sign out front and then changing the sign on every term inside. Now you could proceed to ask the question, what multiplies to make negative 90 that adds to make negative 1? Let's try it. What does multiply to make 90? Now, right off the bat, you might say, oh, I don't want to do a factor table. Right? It doesn't take that long, though. 1 goes into a 90, 2 goes into a 45, 3 goes into a 30, 4 not at all, 5 goes into it 18 times, 6 goes into it 15 times, 7, 8, 9, and 10. Now, I don't expect that everybody is that comfortable with doing lots of division in their head. It's only because I'm super geeky and I've been torturing myself for years that I can just rattle off through those numbers. I would use my calculator. I just use your calculator. Sit there and do 90 divided by 1, 90 divided by 2, 90 divided by 3 until you have all the answers. Now, we want to multiply to make a negative 90, so that means a positive times a negative. So 1 is a plus, 1 is a minus. How do we add them to get negative 1? Yeah, negative 10 and positive 9. And that is the answer. We keep the negative sign out front, and we make our 2 parentheses, and we say x plus 9, x minus 10. And that's the final answer. You've got a negative sign floating out front of x plus 9, x minus 10. Now, by the way, folks, just to convince you that you're not allowed to not factor up a negative 1, what if we had tried the problem, what do you multiply to make 90? It adds to make 1. If you multiply to make a positive 90, that means they're either both positive or they're both negative. If we want them to add to positive 1, that means they both have to be positive. So which one of those pairs of numbers adds up to 1? None of those add up to 1. That adds up to 91, 47, 33, 23, 21, and 19. None of those add up to 1. So if you didn't factor out the leading negative, you would have thought that it couldn't be factored. All right, how's that? So what have we learned so far? The basic factoring technique says, what do you multiply to make C that adds to make B, provided that A equals 1? We've also learned that if you have a leading number, you can try to factor it out so that A becomes 1 again. And if you have a leading negative, you have to factor it out so that A becomes 1 again. So ultimately, these techniques that we've learned only work if A is equal to 1. Okay. Questions before we keep going? We're talking about factoring, which means converting an addition problem into a multiplication problem. This is just a special formula here, the difference of squares. You've probably seen it before. A squared minus B squared can become A plus B times A minus B. And so whatever A and B are, I can use this formula. I can write x squared minus 3 squared, and that's really going to be x plus 3, x minus 3. And if I simplify that, that's just x squared minus 9. So this is a simple rule that only works if you have a square number minus a square number. So for instance, in the case of k squared minus 16, what should I do first? What is 16?
Is it 4 squared?
Yeah, that's 4 squared. So I'd want to rewrite that as k squared minus 4 squared, because now it's very obvious to me that I'm going to use the numbers k and 4. So therefore the answer is k plus 4, k minus 1. And this is just a totally separate rule. It's simple. It's totally different from the what multiplies to make C that has to make B. It's just a visual recognition that if you have 2 square numbers being subtracted, you can write them like this. Now, what is this rule called? It's called the difference of 2 squares. Now, first of all, there's a math joke that says, what do you call it when 2 nerds get in an argument? The difference of 2 squares. Anybody? Yeah. All right, or not. And now, so the difference of 2 squares is equal to, these 2 things are called conjugates. If you have 2 terms, if you have 2 binomial terms that have the same numbers, but one is plus and one is minus, those are called conjugates. So that would be like a plus b times a minus b. Those are conjugates. So the whole rule would be said, the difference of 2 squares is the product of 2 conjugates.
And that's the rule. Bust that out the next time you're on a first date. You're like, oh, well, you know, the difference of two squares is equal to the product of two conjugates. You'll definitely get a second date. All right, so that's the difference of two squares. What's that, Hector? That totally would work on my wife. All right. This next one you're going to skip, slash the whole thing out. It uses the same procedure. So now let's talk about factoring by grouping. This is very special. I want you to take a look up there and tell me 3 ways in which that expression differs from our ideal factoring problem, where A equals 1. So when I say the basic method, the basic factoring method, whenever we do basic factoring, it's just something like x squared plus bx plus c. Right? That's basic factoring. It's the easiest that it gets. And you say, what do you multiply to make c that adds to make b? How are these problems different from basic factoring? Where? There.
You have a second variable.
You have a third variable term.
Yes.
Or in other words, you have 4 overall terms, don't you? Yeah, definitely that's one thing. Normally we start at x squared. These problems start at m cubed, a cubed, and cubed, and so on. So that's one big difference. What else? It's not a 1. Yeah, it's more than 1. And, well, I believe we've already said it. There's 4 terms instead of 3. Okay, so at first glance, does this look anything like this? No, not at all. This is a completely different technique. And yet, it's just as doable in terms of rewriting it as an addition problem. Everyone agrees this is an addition problem? This plus this plus this plus this? It's an addition problem. So now let's factor it. So everyone, let's start with 27. And what we have here is 16m cubed minus 20m squared plus 12m minus 50. I claim that when we're done, it's still going to be a parenthesis times a parenthesis, which should really impress you. Now, I know you've seen this before. You probably already know where we're going. But still, that should really impress you. Then we're going to take this 4-termed addition problem and turn it into something times something. Okay, that's like tantamount to magic. All right. This method is called factor by grouping. And the grouping that you do is you group the first 2 and you group the second 2. This is a wise idea in math and life. If you have a big problem, break it down into 2 smaller problems. All right, so now, let's just focus our attention right here. What can I factor out? First, what can I factor out from the 16 and the 20? A 4. Next, what can I take out of the m cubed and the m squared? M squared, right? Because this has m times m times m, this has m times m. So the most I can take out from both is m squared. So now we write down 4m squared, and now we have to write down what's left. So remember, because this is 2 different parts of your brain, to pull out the 4, we divide. So 16 divided by 4 is 4, 20 divided by 4 is 5. But to pull out the m squared, technically we're subtracting from the exponent. So 3 minus 2 is just m. You can write m at the first, but it's just m. Whereas I took m squared out of m squared, so there's no m term left. Okay, so does everyone feel comfortable saying that the answer is 4m squared outside of 4m minus 5? You have a question? Please ask. Okay, how about the second one? What can we pull out of 12m minus 15? It's just a 3. So we take out a 3, that's division, 4m minus 5. Factoring by grouping only works if when you do what you just did, these 2 are the same. Okay, if those 2 binomials were not the same right now, you would just throw up your hands and cry. No, you would just say, hey, this one's not factorable. Okay, you can't factor this one. These 2 things have to be the same. Okay, so what do we do next? Well, first I'd like to motivate it to make sure that you feel comfortable that what I'm about to do is crazy. Let's say that I had 4m squared y plus 3y. They both have a y in it, so what did I do? What did I bring out? A y. So I bring out the y, and what would be left? The 4m squared plus 3, right? So I'm just taking out the thing they have in common. The thing they have in common is a y. I bring it out front, and what I have left is the bits in front. Okay? So what do they both have in common? The 4m minus 5. So I'm going to bring from the whole thing I'm going to bring out the 4m minus 5. And then what's left? The 4m squared plus 3. And I know I wrote gigantic big brackets. It reduces down pretty far to just 4m minus 5 times 4m squared plus 3. And that's it. So what I'd like you to notice then is when you do factoring by grouping, provided that both parentheticals are the same, they have to be the same, then in your final answer, the 4m minus 5 becomes one of your parentheses, and the leftover bits becomes the other parentheses. That's the procedure. So again, we took a 4-term addition problem and turned it into the product of 2 binomials. We took an addition problem and turned it into a multiplication problem. Is this even the right answer? How could we check? Well, we don't set it equal to 0. That'd be if we were solving for the x-intercepts. You could just FOIL it out. You can just FOIL it out. Which, by the way, is everyone's fourth favorite F word. FOIL. You can't do FOIL on a calculator. Not to my knowledge, anyway. Okay, yeah, you could. But no, not really. Okay, so FOIL. First, that's 16m cubed. Outer, that's 12m. Inner, that's minus 20m squared. Last, minus 15. Is that the original problem? Yeah, the two terms are mixed, but yeah, it's the original problem. So the answer is correct. So that's called factoring by grouping. I'd like all of you to go ahead and try number 29. Try number 29, and then we'll all go back and do number 28 together. So do 29 right now. We're going to slap parentheses around the first 2 terms, slap parentheses around the last 2 terms. You slap. Yeah, you know, slap some parentheses around there.
Like a queen. So slap it.
Like your what?
Like metal and queen.
Clean. Oh, like you slap metal on something. Oh, okay, I see. How about oh, yeah, right. All right. Okay, so we put parentheses around the first 2, we put parentheses around the second 2. Keep in mind what symbol should you have in between your 2 parentheses? What? There better be a plus sign there, right? Because what if there wasn't a plus sign there? That would look like implied multiplication. And we haven't converted into a multiplication problem yet. This is still an addition problem. So what can you factor out of the first term, or the first pair? The 7k squared? Leaving behind 3k minus 5. What can you factor out of the second pair? They're just a 2, leaving behind 3k minus 5. Are they both 3k minus 5? So 3k minus 5 is one of your factors, and 7k squared plus 2 is your other factor. That's it. Well, you can FOIL to check your work, right, to make sure that that's correct. Okay. So that's called factoring by grouping. Now, everyone take a look at number 28. I want you to notice that 28 is pretty different. What's different about 28? What problem might you run into? 21x cubed minus 14x squared minus 9x plus 6. What about the minus? Which one? Yeah, this one right here. Notice if you put parentheses around the first 2, that's easy. How do you put parentheses on this? Do you put it in front of the negative or after the negative?
Oh, so you're adding to it.
Yeah, so that negative has to stay with the 9 because the 9 is negative. It's a negative 9. And so now you have to forcibly put in a plus sign. Because remember, there still better be a plus sign in between your two parentheses. Because we haven't done anything to convert this to a multiplication problem yet. So there had better still be a plus sign in between your two pairs of parentheses. And yes, that 9 had better keep its negative sign, because that negative applies to the 9. Okay, so now the first pair, you can take out what? 7x squared outside of 3x minus 2. Now what about this thing? What can we take out of a 9 and a 6? A 3. Now this negative right here is another leading negative. If you just looked at this, that 9 would be a leading negative, and you have to factor out a leading negative whenever you can. So we're not just taking out a 3, we're taking out a negative 3. And so when you take out a negative, what do you do to the sign of everything inside? Change it. So now that'd be positive 3x minus 2. And it's a good thing because, are they both 3x minus 2? Yeah. So remember, you have to end up with the same parentheses. Because now the answer, the 3x minus 2 is one of your parentheses. And what's the other one?
7x.
Yeah, 7x squared minus 3. All right. By the way, folks, is this all ringing a bell? I mean, you did this at one point. It just could have been many years ago. The what, Hector? Well, I'm not trying to imply you're young or old. You could be 25, and if you did it last in 10th grade, I mean, that could have been like 9 years ago, right? So, yeah, I'm not saying that anyone in here is old, just that it could have been a while. All right, so that's factoring by grouping. This last one is so cool. It's so brilliant. It's so amazing that someone even came up with this. And that's what I really want to impress you with, is the sheer ingenuity. Okay, I'm going to leave that there. The sheer ingenuity of coming up with this problem. So everybody, let's write down number 31. 3b squared plus 13b plus 4. Now I'd like us just to think for a minute, what could we try on this problem? First of all, is the first term a 1? No, so we cannot do basic factoring. Even if we tried, it would be hilarious, because what multiplies to make 4? 1 and 4, 2 and 2. Do either of those add up to 13? No, there's no way, right? So there's no way to do that. So we can't do basic factoring. Can we divide a 3 out of everything? 3 doesn't go into 13, 3 doesn't go into 4. So you might look at this and say, we're completely stuck. There's no way to factor this problem. But what if I just randomly said, instead of writing 13b right there, let's rewrite 13b as 1b plus 12b. Is that fair? Is 13b equal to 1b plus 12b? Everybody try it. 3b squared plus 1b plus 12b plus 4. Now keep in mind, the only reason I knew to rewrite 13b as 1b plus 12b is because I received inspiration directly from heaven. An angel told me to rewrite that as 1b plus 12b. Okay, so now, can we factor by grouping? And what do we take out of the first pair? Just a v, so there's v outside of 3v plus 1. And then what can I take out of the second pair? Just a 4, so that's also 3v plus 1. Are they both 3v plus 1? So one of my parentheses is 3v plus 1, and the other one is v plus 4. Now, that was pretty lucky. I suggested we rewrite 13b as 1b plus 12b, wasn't it? Now, can you just rewrite 13b in any old way you please? Like, what if I instead said 3b squared plus 13b plus 4, and I said, let's rewrite 13b as 3b plus 10b. You could have tried it another way too. I just already have this way in my head. Yeah, you can rewrite it any way you like. Let's see if it works. Here and here I can take out a 3b, and that leaves me with v plus 1. Here I can take out a 2, and that leaves me with 5v plus 2. It doesn't work. So it's a good thing I received my inspiration to know that it was 1v plus 12v. But what we'd like is, how can we know how to rewrite 13b in the right way? And that's what we want to know. Because our goal, anytime you cannot factor out the leading term, that's not a 1,
how can you rewrite the middle term in the right way that will lead to factoring by grouping? And the brilliant answer is that you multiply the first term by the last term. 3 times 4 is 12, and you do a factor table, and you say, when you multiply A times C, well, what multiplies to give you A times C? That adds to give you the middle term. It's almost the same question as before. So what multiplies to give you 12 that adds to give you 13? 12. And that's how I knew how to rewrite my 13. So notice this is very different. It used to be that when we did a factor table, those two numbers became our answer, right? In basic factoring, those numbers became our answer. In this context, those answers are not becoming our answers. Those answers are simply telling us how to rewrite the middle term so that we can factor by grouping. So notice, we're still using a factor table, but in a completely different way. These numbers now are simply how to rewrite the middle term so that we can factor by grouping. Okay, so we've completely done number 31. Let's move on and try 32.
So the angel who told you
The angel who told
this was Lucifer?
No, it was Angelus Factoris. No, I don't know. Okay, so let's try number 32. In number 32, we have 5n squared minus 7n minus 24. Now notice, we cannot use basic factoring. The a term is not 1, it's a 5. And can we factor a 5 out? No. Okay, so we're stuck. So we want inspiration to rewrite our middle term. Okay, that's our goal. If we could rewrite the middle term in a clever way that would allow us to factor by grouping, we'd be done. So multiply a times c. What's 5 times negative 24? Yeah, negative 120. Now right here, I know that I might lose some of you. Because you'll say, I don't want to do a factor table for 120. Right? But the fact is, it doesn't take that long. And you can use your calculator or in your head, and you say, okay, 1 and 120, 2 and 60, 3 and 40, 4 and 30, 5 and 24, 6 and 20, 7 and nothing, 8 and 15, 9 and nothing, 10 and 12. Okay, now, the only reason I know that is because I've done that factor table a lot. Okay? So I don't expect you to just rattle that off. I expect you to use a calculator. So what we want is two numbers that multiply to make negative 120, so that means a positive and a negative, and they have to add up to negative 7. So you scan down the list for two numbers whose difference is 7, and it would have to be a negative 15 and a positive 8. Now again, remember, this is not our answer. We don't just go somewhere and write down n plus 8, n minus 15, because that's not what we're doing right now. That's only basic factoring. This is how we rewrite the middle term. So now the question is, can I write plus 8n minus 15n, or can I write minus 15n plus 8n? It doesn't matter. You can write it either way. And I would be strategic and put the negative term first. So 5n squared minus 15n plus 8n minus 24. Why did I put the negative term first? Yeah, so this one's already positive. So now we slap some parentheses on the first two and on the second two, and we begin factoring by grouping. So what can I factor out of the first pair? That 5n, leaving behind n minus 3. Now what can I factor out of the second pair? Yeah, just an 8, leaving behind n minus 3, which is a very good thing. They're both n minus 3. So one of my parentheses is n minus 3, and the other one is 5n plus 8. Yep. Now, I will admit, that is a lot to cover in just one class period. That's to review all of the factoring situations you've ever encountered before in your life. And I gave you lots of extra practice problems in that packet, and I even gave you the answer key at the end. Wait, didn't I? Yeah, the answer key is in the back.
Yeah.
So I would recommend you go ahead and go through and finish all those. Try them on your own. I'm not going to collect it, but I think it's very good practice, especially since I gave you the answer key. Okay, so what did we just accomplish? We just accomplished turning addition problems into multiplication problems so that we can factor a quadratic and solve for its equals 0. Okay, I have a whole, when does class get out? Oh, 15?
Yeah, you have like 30 minutes.
Oh, fantastic. That's very good. Boy, I thought class was almost over. Okay, everything's great. Life is good again.
What are we prepared to that's on
Yeah, the class is Monday of next week.
what do you think? Like what are we committed to take with us? That's
Your pencil and your calculator. Yeah, pencil and calculator. Okay, so go ahead and turn to the next packet.
are
This
we
one.
allowed, like are we allowed notes?
No.
No, we
No notes or formats.
You'll most likely provide what, side notes, or like not side notes, but scratch paper?
Yeah, you can have scratch paper, but I would rather you show off your work on your paper because that's how I give you credit.
And the formulas will not be given.
Correct. No formulas will be here. I'll consider it, but I don't think so. I want you to look right here at the squares packet, which I think is just next, right?
Yes.
Yeah. Okay. So first of all, this whole page here is just a friendly practice page for you because my recommendation for you is that you learn the first square numbers 1 through 20. So I would like to encourage you. So just look. That's 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, all the way up to 18 squared, 19 squared, 20 squared. And I really encourage you to spend the next couple weeks of your life practicing, memorizing all of your square numbers from 1 to 20. You're waiting in line to order food, practice your squares. You're taking a shower, practice your squares. You're brushing your teeth, practice your squares. If nothing else, I'd like you to just recognize, like if you saw 225, you say, oh, that's a square number. I don't remember which one it is, but it's a square. Right? So you want to have visual recognition, but ideally you'd memorize it. So that whole first page there is just for you to practice, practice memorizing your squares. Okay, that's that. Let's turn the page. Where's my mouse? Oh, I never put it. Okay. Next, your square roots. Square roots are just the opposite of your squares. So on that number line right there, start it with me, folks. It's helpful to have a number line and to practice doing it, that this is actually the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4, and so on. This is, honestly, they're the exact same facts, but they're just written backwards as square roots instead of squares. Again, it's helpful to be able to recognize it. At the very least, you can make this number line and then go through the page, testing yourself. You probably know all the little ones, like the square root of 25 is 5, but maybe try recognizing the square root of 196. And the more you look it up, the more likely you are to memorize it. So this whole page is just a gift from me to you, a gift, so that you can go home and practice memorizing your squares and your square roots. Okay, turn the page. You can cross this page out, Critical Math Party. It's a good page, but we don't have time. I just threw that in as a bonus anyway. Let's go to here, simplifying roots. This is a very important skill. When you are given a square root,
We're just crossing out the math party one.
yeah, you can cross out the math party one. You can go home and try it on your own. Or we can talk about it in office hours, but we won't cover it in class. So, how do you simplify a root? Everybody look at the very first problem, root 20. The square root of 20. First of all, is there a number that you can square to make it 20? No. If you do it on your calculator, the square root of 20 is error. Well, no, not error. That would be hilarious, though. That'd be funny. Every time you get to a calculation you don't want to do, you're like, error. It's 4.472135. Now, technically, there are infinitely many decimals, but more likes 4 decimals of accuracy. So there. That would be the square root of 20 to the accuracy required by more. Not a very clean answer. Nothing you can do off the top of your head, right? However, it is possible to simplify the square root of 20. Let's talk about the word simplify. What do we mean to simplify the fraction 20 12ths? You just make it smaller, right? So what can I take out of 20 and 12? 4. Yeah, 4. So I divide 4, I divide 4. That gives me 5/3, right? So we say that that fraction is now simplified because the numbers got smaller. So root 20, it is possible to make the 20, the number inside the root, smaller. So what do? And this only works for certain numbers. You look at a 20 and you say, is there a way to rewrite 20 as the product of two numbers where the first one is a square number? So everyone look at this number line of square numbers I just gave you. This is the technique. You find 20 where 20 would be. 20 would be there between the 16 and the 25. And you work your way to the left looking for a number that divides into 20. So starting here, does 16 go into 20? Does 9 go into 20? Does 4 go into 20? Yeah. So we're going to rewrite 20 as 4 times 5. Now why would we do that? Because there's a rule that states, this is just called the product rule for roots. If you can rewrite a square root as two numbers being multiplied, you can separate the root into root 4 times root 5. You're only allowed to separate a root over multiplication. And that's called the product rule for roots. It's right there on your paper. It says, second, know the product rule for roots. The square root of m times n is the square root of m times the square root of n. That's the only time that we can separate a square root is across multiplication. So now that we did that, what's the square root of 4? 2. And so the answer is 2 root 5. We call this simplified because the number under the square root got smaller. You'll notice now there's a number outside the square root, but that's okay, that's just a whole number. People are comfortable with whole numbers, but a square root we'd like to simplify. Now, type that into your calculator just to convince ourselves, what's 2 root 5? You just type 2 root 5. Exact same number. Right, so for sure, the square root of 20 is equal to 2 root 5. But the difference is that 2 root 5 is what we say is simplified.
What about 2 root 4? I mean 4 root 5.
What about 4 root 5?
Oh,
Square root of 4
okay,
is
yeah,
2.
right, yeah.
Oh, okay. Emily.
Is there a way we can do like the factor?
Yes, you can. I'm not going to do that method myself in class because this method allows you to do variables as well. Well, you could do the factor tree method with variables too. Folks, you might be familiar with doing the square root of 20 by doing the factor tree for 20. And you'd say 4 times 5, which is really 2 times 2 times 5. So you would say 2 times 2 times 5. And anytime you have a pair of numbers, you get to take it out, and it becomes 2 root 5. Yes, that method is accurate.
You want that method to be?
I want you to be able to simplify from there to there. So if you do it that way, I'm okay with it, but I'm going to demonstrate this way in class. Okay? So you can do it this way if you want, but I'm going to be showing this way. Okay? So now, everybody, let's try that method a couple times. Let's try the square root of 63. I would like to simplify the square root of 63. Now keep in mind, in order to even do this, you either have to have the square number line out in front of you, you need to have a list of squares in front of you, or you have to have it memorized in your brain so you can see it. Like close your eyes and look. But no, easier if it's written down. So find 63. 63 would be there. And then you start working your way to the left, finding the first number that goes into 63. So what's the first number that goes into 63? Yeah, 9. 9 was the first number that goes into 63. How do you know that? You take out your calculator. What? What's because of Lee? Oh,
It's because I was for 9. Sorry.
Oh, well, yeah, that's fine. So yeah, so 63 is not divisible by anything until 9. So now we say 63 is really 9 times 7, which is root 9 times root 7, which the square root of 9 is just 3, so it becomes 3 root 7. Now, sometimes it's easy to find the number that goes into it. Sometimes it's not so easy, like 80. Again, you might need your calculator out to actually sit there and divide. So you find 80, and then you start working your way to the left until you find the first number that's divisible by 8. Or sorry, that goes into 8. Yeah, and it is 16. See, that's not obvious right off the top of your head. You might keep going until you hit 4. You're like, oh, 4 goes into 80. But you would have passed over 16. And that's why it's important you have a calculator out. You check each one. So 80 divided by 64, no. 80 divided by 49, no. 80 divided by 36, no. 80 divided by 25, no. 80 divided by 16 equals 5. So you'd say root 80 is really root 16 times 5, which really becomes root 16 times root 5, which the square root of 16 is 4, and the answer is 4 root 5.
Did you square root that?
Well, there's no square root symbol over the 4 right now. Yeah, you only do the square root once. But your question is a good one. I've seen so many students do that, where they have a question like 256 and square root of 256 is 16, And they're like, hey, I just square root of 16. And then they do it. And they're like, hey, I just square root of 4. And then they do it. And somehow they get all the way to 2. And like, no, you just do square root once. Okay? Yeah, but it's a great question, Hector, because people do it. Okay. So that's it. Now, what about a number like 30? 30 is not up there. Well, let's try the square root of 30. What's the first square number that goes into 30? You find 30, you start working your way to the left. What goes into 30? 1. Well, 1 is completely useless. Because if I rewrite that as root 1 times root 30, it's still 1 root 30, which is just root 30. So you look at root 30 and you say it's not simplifiable. Just like some fractions. If you have the fraction 2/5, can you simplify 2/5? No. Can you simplify root 30? No. It's just not simplifiable. Also, just so you know, if you just randomly took any number from 1 to 100, like you just reached in and grabbed a number, will it be simplifiable root? Only 10% of the time. So not very numbers are actually simplifiable in general. So like if I just randomly chose a number like 31, not going to be simplifiable. This one's not because it's not divisible by it's a prime number. The point is, it's just something you have to double check. Anytime you have a square root, you just have to double check against the off chance that it is simplifiable, even though it might not be. Okay, so that's how you simplify a root. And you now have the standing mathematical command that for the rest of your life, whenever you see a square root, you have to simplify it. We're skipping over the imaginary number portion, and we're going to the quadratic formula packet. So now flip over to the quadratic formula packet.
So the imaginary numbers are on the test?
No, it's not that they won't be on the test. We're just not going to do it right now. Okay, so, but I will double check that, Hector. I think probably there are no imaginary numbers on the test, but I'll tell you right now, whatever's on the practice test will be on the test. Okay, so first, everybody write down the quadratic formula. So remember, given ax squared plus bx plus c, the x-intercepts are negative b plus or minus root b squared minus 4ac all over 2. And really what I should say is given ax squared plus bx plus c equals 0. As we're saying, you know, in general, if you have a function and you set that function equal to 0, it's going to tell you the x-intercepts. So that's what we're doing. You're taking some quadratic, you're setting it equal to 0, and you want to be able to solve for the x-intercepts, and that's your formula. So remember, your x-intercepts for a quadratic, if it's the plus or minus, the right-hand root is negative b plus root b squared minus 4ac all over 2a, whereas your left-hand root is negative b minus root b squared minus 4ac all over 2a. That's what the plus or minus is indicating. The right-hand root and the left-hand root, or the larger root and the smaller root. That's how the Moore program describes it. That's the larger x-intercept. That's the smaller x-intercept. All right. So what we'd like to do is, how can we use the quadratic formula to find x-intercepts? So first, let's write down 2n squared minus 8n minus 120. And right now, don't write this down, but right now you might go ahead and say, oh, my a value is 2, my b value is negative 8, and my c value is negative 20. I'm sorry, negative 120. Well, what could I do to that whole equation first? I can factor out a 2. And if I factor out a 2, then what I really have is 2 outside of n squared minus 4n minus 60. And since there's a 2 out front, what can I do with my 2? Not subtract. Yeah, I can divide both sides by 2, and now I have an even easier formula, n squared minus 4n minus 60 equals 0. And now my a is 1, my b is negative 4, and my c is negative 60. So what do you think? Should I do that? Yeah. Yeah, I mean, why not? You're about to do the quadratic formula. It's helpful to have smaller numbers, not bigger numbers.
So that's what you do whenever you can. Just like before, you want to factor out a leading term if you can. Okay, so now we're going to do the quadratic formula. So first, you write down the quadratic formula just once, negative b plus or minus the square root of b squared minus 4ac all over 2a. You write it down once so that it's on your paper and it's right there and you're about to look at it to do your problem. So then you write it down a second time blank. You write it empty. So negative b plus or minus the square root of b squared minus 4ac all over 2a. You write it empty so that you have a spot to put all those numbers. Again, this is just my best practice. If you have a way that you feel comfortable with and you can get the answer every time, then great. But otherwise, I would suggest writing it empty. Now carefully plug in the numbers. B is negative 4, B is negative 4, A is 1, C is negative 60, and A is 1. What's the hardest part about doing the quadratic formula? Yeah, all those negatives and doing it right. So now what do we have? Negative 4 is really 4 plus or minus the square root. 4 squared is 16. Negative 4 times negative 60 is plus 240 all over 2. Okay, so now that's 4 plus or minus root 256 all over 2. And now, after you've been practicing your squares for a while, you'll look at 256 and say, hey, I recognize 256. It's a square number. What square number is 256? You might have to go back and look at your square number list.
15.
No. 16. It's 16. So the square root of 256. Now, of course, you can just type that into your calculator. So if you type that into your calculator, you're going to get 4 plus or minus 16 all over 2. Now, it's at this point that I encourage all of you to follow my lead and split that into two alternate realities. You say, okay, it's 4 plus or minus 16 over 2. So on the one hand, that could be 4 plus 16 over 2. On the other hand, that could be 4 minus 16 over 2. Those are the two possible realities. More importantly, those are the two possible x-intercepts, one on the right, one on the left. So 4 plus 16 is 20 over 2, which is 10. And 4 minus 16 is negative 12 over 2, which is negative 6. And so our answers are 10 and negative 6. What do we mean those are our answers? Those are the x-intercepts. Those are the numbers I can plug into the equation to make it true. Now, by the way, I'm sure you all wanted to do this for fun. If you started with 2n squared minus 8n minus 120, I could also factor this problem. I could factor out of 2, n squared minus 4n minus 60. And then I could say, what multiplies to make 60? That adds to make 4. And the answer would be, yeah, 10 and 6. Very good. So 10 and 6. One of them will have to be negative, one positive. So now that would be 2 times n minus 10 times n plus 6. And then I say by the zero product rule, this times this equals 0. So either that or that must be 0. So n minus 10 equals 0, or n plus 6 equals 0. Either way, this means n equals 10, and this means n equals negative 6. Did I get the same answers? Yeah. Now you might say, Mr. G, why on earth would I do the quadratic formula if I can just factor? I think that's a good point. I think factoring is faster. But not every problem is factorable. Sometimes you'll get to a problem and you're like, oh, it's not factorable. So that's why you have to use the quadratic formula. The quadratic formula is your backup plan for when you can't factor. Or maybe you just prefer the quadratic formula. You're like, you know, Mr. G, I don't want to do factoring for the rest of my life. You never have to. You can just do the quadratic formula. Unless you're taking a test that says factor. Hector.
Yes, the quadratic formula is very good. But look what you had to do before you could use the quadratic formula.
You mean factoring out the 2?
Yes.
Well, I could have just used the numbers 2, negative 8, negative 120. Yeah. But no, you have a great point, Hector. I mean, everything is a give or take, right? Like, it's all choices that you make. I can either solve the problem with quadratic or I can solve the problem with factoring. It's a personal choice that you make.
You couldn't use it if it was like the 4 value number like how we saw.
Right. You're right. You could not use the quadratic formula to do factoring by grouping. Okay. So, folks, here's what I'd like to do next. I'd like to do, not number 2, skip ahead to number 7. Let's do number 7. So skip ahead. We're going to do number 7 together. So here we have 3n squared plus 10n plus 5 equals 0. And what that tells us is that a equals 3, b equals 10, and c equals 5. That's a best practice to label your values of a, b, and c. Okay, then we write x equals negative b, or if you have it memorized, you can write negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay. Now we're going to go ahead and plug in all of our numbers. So negative b plus or equals plus or minus square root of b squared minus 4ac all over 2a. So we're plugging all of our numbers. And now we begin baby stepping our way towards the answer. Negative 10 plus or minus the square root of 100 minus 60 over 6 is negative 10 plus or minus root 40 over 6. So when you get there, just look at what we have right there and ask yourself, can I simplify that? Like for instance, are all the numbers divisible by 2? So you might be very tempted to divide all those numbers by 2. However, you're not allowed to divide a 2 into a square root. It's a square root. That number is kind of like sectioned off all by itself. You can't just divide a 2 out of the 40 right now because it's underneath the square root. So instead, what would we have to do to that square root 40? Yeah, we have to simplify it. We have to break it up into the 2 bits. So what square number goes into 40? You might want to have your list out in front of you. What square number goes into 40? Yeah, 4 and 10. 4 is the first square number that goes into 40. If you look back at your list, 4 would be the first number that goes into 40. So on a separate piece of scratch paper, do root 40 is really root 4 times 10, which is really root 4 times root 10, which is really 2 root 10. So now we could go ahead and write that. We could say negative 10 plus or minus 2 root 10 over 6. Okay, so again, we can't touch the 10 under the square root. That's a separate number. But we do now have whole numbers, and they're all divisible by 2, and we'd like to divide all those whole numbers by 2. The safest way to do that is to factor a 2 out of the numerator, right? Because the top I can factor out a 2. So the 2 would come out, and that would leave behind a negative 5 plus or minus 1 root 10. First of all, do you all agree with it? And I factor a 2 out of the 10 and the 2. Yeah, that 10, not that 10, this 10. I can divide both of those by 2, so I bring the 2 out front, and now what? Yeah, both the 2 and the 6 are divisible by 2, so 2 goes into 2 once, 2 goes into 6 3 times, and we're left with negative 5 plus or minus root 10 all over 3. And that is what we call simplified. That is as simple as it can possibly be, because the root 10 cannot break down any further. There is no square number that goes into 10. Tell me. Well, there's a 10 and a 2 right here. Oh, like here, man, watch. What if I had negative 10 plus 2x? Could I factor 2 out? How would I do it? Yep, and I'm treating the root 10 like an x. Oh. So I just pull the 2 out. Okay. Okay, well, folks, there we go. So that is a very helpful tool to be able to simplify a root because it allows you to simplify a quadratic. So that was my 5-minute there. Let's just see here. That completes section 2.4 and 2.5. So if now I go over here to more, and when you go home, and you're going to go in and start your homework for 2.4 and 2.5. I hope you all start it tonight because it'll be fresh in your mind. Here's module 2. You go down to section 2.4 and start your assignment. Now you'll notice, I believe they're all pretty straightforward. These are all the types of problems that we did in class today. You'll be able to use the basic factoring technique for most of it. But then there will be a couple problems towards the end that you have to do the longer method of factoring by grouping. Keep in mind, you can click on the video button or you can email me and I'd be happy to reply and help you. So that's section 2.4, and then section 2.5 is the quadratic formula. So when you go to do section 2.5, the questions are each going to ask you to solve using the quadratic formula. Or the zero product rule. So everybody, like, take a look at this first one. They're asking you to use the zero product rule. So this one is already factored. It's x times x plus 17. And we're saying that's equal to 0. So since they're being multiplied, one of them has to equal 0. So you'd say, well, either x equals 0 or x plus 17 equals 0. And that's just the basic zero product rule. So all that section is either going to be the zero product rule or the quadratic formula. Okay. Notice there are a couple problems where they give you a root expression and they want you to simplify it like we just did. Let me show you that one. So they have 25 minus root 125 all over, what is that, 5? So what square number goes into 125? 25. So we'd rewrite that as 25 minus, no, I'm going to do some scratch work. 125, that's really 25 times 5, which is really root 25 times root 5, which is really 5 root 5. So now I have 25 minus 5 root 5 all over 5. And again, from the numerator, I can just factor out a 5. So it'll be 5 outside of 5 minus root 5 all over 5. And the 5's completely cancel out, and I'd be left with just 5 minus root 5. So that simplifies a lot. And by the way, folks, how do you type in square root? SQRT, 5 minus SQRT 5. I hit submit, and that's the answer. Okay? So I know that class is over. If you have any questions, please email me. Today was what? Was today Monday? Yeah. Oh my gosh, today's Monday. So I'll see you Wednesday. Yeah, for a second there, I would have been convinced it was Wednesday.
Felt like we were advanced for like 2 days last week.
Oh, yeah. So, Lee, at the beginning of class, you asked me what my favorite method for factoring was, or what my preferred?
Yes.
So anyway, what's your favorite?
What is it called? Square? Solve by square?
Oh, completing the square?
Yeah.
Oh, okay. So is that traditional what you do when you have a quadratic? You do the complete the square?
Yes.
Wow. I'm impressed because that's, I mean, it's somewhat more steps maybe, but I mean, it's a very good solution.
Hey, at least you're not forgetting your one,
That's
right?
awesome. Yeah, completing the square.
To me, it's faster.
Really? Yeah. I get it.
Because you're just doing the same thing.
Right. Yeah, you are. You're just doing the quadratic. Huh. And then, but what about when you get to a problem that has a not equal to 1?
A not equal to 1?
Yeah.
I just divide it out and then I rock it that way.
Oh, okay.
And so, like, are you saying, like, if I had, like, let's say 3x squared, do something.
Plus 5n.
Plus 5x.
Yeah, plus 7.
All right, plus 7. All right. So then I just wrap the 7 across. So 3x squared plus 5x equals negative 7.
Yeah, yeah.
I divide all that by 3.
Yeah, yeah.
And then there I have x squared plus 5 thirds x equals negative 7 thirds.
Yep.
From there I just divide this guy by 2.
Hey, okay, that's awesome, Lee.
Yeah, so basically if you do that 6 underneath and it's just easier to rock.
I'm
Yeah.
gonna be on campus Tuesday, and Wednesday I will also be on campus. So I was wondering if
I like
huh?
Yeah, I like that too, Lee. That's very cool.
So I don't want to set a appointment because I know it's gonna happen tomorrow. So maybe if you're there, I'll just drop by and see.